on the objectives, you'll see number 11 says, calculate the amount of heat required to increase the temperature of a mass. This is the heat required to raise that temperature of a mass. That equation by itself isn't usually going to get us anywhere. This is just another form of energy. And just like we saw with kinetics and potential energy, all those energies and work we put into one main equation that had all those things in there. We're going to do something similar with these. So this by itself will just kind of be a piece that's going into a bigger equation, but on the objectives it is kind of stated out as just one statement there to find the heat required to increase the temperature. What we're going to see though is that there's going to be sometimes more than just one single Q. There will be more than one mass in the problem, so we'll put them all together and look at everything in a container or in a room or something. So it'll be very, very common that we have not just one single Q, but we'll have a variety of these. Okay? Maybe all of that similar form, but there usually will be more than one mass. Okay, let's talk about phase changes now. What we really need to check for is when we're talking about heat and the energy transferred due to heat, we're going to just be asking ourselves, is there a temperature change? And if there is, we have these kinds of Q. And then also, is there a phase change? And a phase change meaning a change from the different phases of matter, solid, liquid, or gas. And that's what we talk about here with these phases. To discuss the phases, we need to define the latent heats. So for a solid to liquid or liquid to solid phase change. The latent heat for this phase change is called the latent heat of fusion. And we use an LF for that latent heat. The latent heat is really just a measure of the amount of energy that you need to change the phase of a mass. It's going to have units of joules per kilogram. In your book, you will see a table on page 395. And you'll see right on there the latent heats of fusion for some different substances there. There's quite a few different things listed in that table, so open that up and look at that page 395. You see the LF there. You have units of joules per kilogram, but also units of kilocalories per kilogram. Again, we're going to stick with joules per kilogram most times. You can use those other constants there in kilocalories if you want to, if you had units of calories that you wanted to work with. But more often than not, we're going to be sticking with the joules per kilogram and then the joules per kilogram per degree Celsius over there for our specific heats. Okay. So the latent heat for a liquid to gas or gas to liquid phase change is called the latent heat of vaporization. And you'll also see that same value or table for those values in the same table on page 395. And then you'll see there that's going to be written down as an L with a V for vaporization there on the subscript. And you have all those values there in the table also. You should also notice on there that you have the melting point and the boiling point for all those substances. Those melting and boiling points are important You'll need to know what those are, because if I want the energy that's required to, let's say, melt some ice, then you need to know what its melting point is. So the energy required to change phase of mass is Q is equal to plus or minus m times L. The m just being the mass, the L being either the LF or the LV, the latent heat of fusion or vaporization, depending on what kind of phase change you have. The plus or minus is for heat flow into the system, or minus for heat flow out of the system. The same plus or minus sign convention that we used back with the other Q. Positive if you're adding heat, negative if you are removing heat. On these Qs, and it's the same Q, we don't have a different subscript for it, it's just another form of heat here. On this one here, you choose the plus or minus signs on your own. The other one, you just trust your math, put in the delta T as final minus initial, and it works itself out. But here you should be thinking about the plus or minus sign on these to then choose those values. So with those melting points and the boiling points, as I was saying, are very useful to have in that table, and you need to know what they are, is that if I asked you for the amount of energy that you need to melt some ice, then you'd say, okay, if I have a kilogram of ice and I have the latent heat of fusion, you could plug in the mass, you could plug in the latent heat. But if you're not already at the melting point, then you can't just take the energy to melt the ice and melt it before it's ready to melt. So say your ice has a melting point of 0, which it does, and you're at -5 degrees Celsius. Before you can actually melt it, which would take this much energy, you need to warm it up first to the boiling or to the melting point, and then you have energy for this also. So when we go through these processes of changing the phase of something, unless we're already at the point where the phase will change at either those melting or the boiling points, then we may need to change the temperature via this Q before we get to the possibility of having a phase change. Okay? And so we'll see how that works later on, but there's definitely times where we'll go through that process where you might take ice that starts at -5, warm it up to 0, melt it all, and then warm it up in a container of water that ends up at room temperature. So it might go from -5 all the way up to room temperature. And you can't just go, well, Q is equal to MC delta T from -5 up to 20 with the temperature change of 25 and not account for this. And you also can't just do this Q to melt the ice and not account for warming it up first and then warming it up to room temperature once it's been melted. So we've got to look at all those different phases there. We're going to have phase diagrams, graphs that really help us look at the separate different phases that we talked about there. Those will be useful in really keeping track of all the Q's that we have. You'll see number 14 says to sketch a typical phase diagram, and we're going to do that coming up soon. Number 12 says apply the method of mixtures to solve a calorimetry problem involving changes in temperature. We're going to do that in lab today. If you watch the video, you know we're going to basically take a heated mass, put it into a container of water, let that energy transfer from the heated mass into the water, come to equilibrium, and really we're going to measure how that temperature changes, and we'll be able to solve for the specific heat in the lab, whatever that metal is. But that's just a transfer of energy from the heated mass into the liquid, the water in our case, through the lab. Okay, these are all really just things looking about the energy transfer between these two forms of energy right here. We will also look at the conversion between mechanical energy and heat energy. And that's another objective on there that we'll talk about, probably not until next time, but this was all just heat right here. We've learned before about things like potential energy and kinetic energy. Just to kind of tell you where we're going with that, that when I push this across the surface, what happens when you rub two things together? Friction. And what do you feel from friction besides just your hands rubbing together? You feel heat, or you feel temperature. And what you're feeling when you feel a temperature difference here, you feel some transfer of energy from one to the other there. You would have some heat loss there from the friction that you had there. If I took a pen or a rock or a stone or an asteroid and let it fall into a lake or a pond or a cup or something, I have all this energy that I'm having something fall from the sky, and that goes from potential up here to kinetic down there, and then it just stops. And energy is conserved, it can't just go away completely. That energy that stops from the collision there goes into maybe the water. And so what would happen to the water? It would heat up. So we're going to see how that we can use mechanical energy, things like kinetic energy or potential energy, things like we've learned about before, and how that can be used or transferred into things like heat energy. Okay, and we'll do that next time. Right now, though, it's just those two new cues that I wrote down for temperature changes and phase changes. We're getting very close to the last equations that are new that I'll write down this semester. There aren't going to be that many new ones next time. This homework set that you're working on now is a lot about you applying these equations to different situations and putting them all together. And individually, they're just simple equations, but if, like I told you before, we might have 2 or 3 or 4 of these to deal with in the same problem. Okay? But it's going to be a lot about those. We will relate that to kinetic and potential energy, but that's nothing new in terms of equations. And as I look down the objectives, 10 through 15 is all about heat and these forms of energy. Okay? 16 is a definition. The first law of thermodynamics is an equation, and there's an equation for the efficiency of a Carnot engine there at number 19, but there's a very good chance that we won't get to the engines there at number 19, so this is really the bulk of what you're going to need as far as equations for this current homework set. We're going to be looking at this a lot for the next full class here now, and part of next time also. Okay? So let me give you some problems. We're going to start with one on calorimetry.